In this video, I'm going to work through this proof. So I have a one-to-one linear transformation, and I have a subset of V that's linearly independent, and I want to prove that the image T of V1 up to T of Vk, which is a subset of W, is linearly independent in W. So let's go ahead and start by assuming our hypothesis. That is that this is a one-to-one linear transformation, and this is a linearly independent subset of V. So I've gone ahead and written that down. I'd like to show that this set is linearly independent, so I should assume the following. As always, I should just assume that I have a linear combination like this that's equal to the zero vector, and I want to prove that each of these scalars is equal to 0. Now, T is a linear transformation, so that means that all of the scalars can come inside, and it also means that T can come outside the sum, so I can rewrite this. So since T is linear, I can rewrite it like that. So let's rewrite that. Since T is a linear transformation. But now I have T of this is equal to the 0 vector, and what that means is that this is in the kernel of T. So I've gone ahead and written that down. So this is now in the kernel of T, but one of our hypotheses was that T was one-to-one. So if T is one-to-one, that means the kernel of T contains only one element, and that's the 0 vector. So that means that this must be equal to the 0 vector. So I've gone ahead and written that down. Since the kernel is 0, and this is clearly in the kernel because it maps to 0, it has to be exactly equal to the 0 vector. But this set is linearly independent. So if that set is linearly independent and we have this linear combination that's equal to the 0 vector, that tells me that each of C1 through Ck must be 0. And that completes the proof because that is what we set out to prove, right? We assumed this was equal to 0 and we wanted to prove that each of these were 0. And so we get our conclusion that, in fact, this is a linearly independent set. So I've gone ahead and I've written out the conclusion, and that completes the proof.